Hey guys, Assalamualaikum warahmatullahi wabarakatuh. I hope you can hear me. Anybody, please respond so that I know.
I can hear you.
Yes, thank you. Because just now I was having a bit of a problem, so I'm not sure whether I'm connected. Okay, guys. Happy New Year. We are already in the year 2021. 2021. Wow, how time flies. Hopefully, this year is will be much better than last year, and everybody will be able to see face to face with you guys. It was in the news that you will be able to come to UTM or be able to have your lecture face to face by March this year. So hopefully that will materialize. Anyway, so today we're going to we're going to continue with what we have covered. For those who haven't scanned I'm going to share with you the barcode. Oh, what happened here? Your computer went to sleep? So what am I supposed to do? Do I need to refresh it? Let me see whether I can refresh it. Oh no, I guess I have to do it later then. Let's see whether I can. Okay. Oh dear. No, later on then. I will do that later on. Okay, guys. Let's recall what we have covered so far. I'm going to show it using my iPad as usual. I need to connect it first. Okay, how many of you are here with me? Let me see. Participant, how many participants do I have? Okay, there's 22 of you. I don't know any more coming. Not sure, hopefully there is some more coming. Okay, let's see whether I can get connected using my iPad. How's the reception over there? Right now, I'm using Wi-Fi. I cannot use the direct line. I'm not sure why. That's the problem just now. I'm using Wi-Fi. And what's wrong here? Why is it that I'm not able to connect using my... Okay. I hope I can connect. Why is it not connecting? Oh dear. What are we going to do if we can't connect? Okay, good. It's connecting. It's a bit slow. I'm using the Wi-Fi. Okay. So far, I need to recall what we have covered. Okay. So I'm going to scroll up so that we can see the very beginning of the slide. We need to refresh back what we have covered last week. I hope you guys can, the reception is good, it's not lagging. I hope it's not lagging. If it's lagging or is it broken, please inform me because I have no idea what's going on the other side. Okay, so we have done, we have looked at on how to calculate the heat of reaction. Okay, for example, this is your reaction, your equation for the chemical reaction. This is your chemical reaction. Yeah. So in order to calculate your energy balance, we need to calculate the heat of reaction. Normally we have it as standard, which is at a temperature of 25 degrees C and 1 atm. Yeah. So now I'm doing just how to recall back what we have covered. So you have three methods of doing to calculate the heat of reaction. If it's not given, normally it is given, but sometimes it's not given and you have to calculate it. So the way to calculate it is either you can use his law. His law, you guys are very familiar with it. You have done a lot of it. Besides this in other subject too. You have another method of doing it. This is the first method. The second method of doing it is using the heat of formation, which you can get from Appendix B1. No, Appendix B1. Yeah, B1. And then the other method is using the standard heat of combustion. So let's look at it, the standard heat of for our formation. If you're going to use the standard heat of formation, which we denoted as delta H with the cap and the superscript 0 and the subscript F subscript F for heat of formation. If you're going to get your heat of reaction using this method, then the formula is, because you're going to form your product, so the first submission will be for the product. You have the coefficient, okay, times by the heat of formation which you can get from your appendix minus the summation of your reactant. Let's write it in full. So this should be your product. Your coefficient, which is the number in front of the formula or the formula. Your heat of formation, which you again can get from the appendix. So what is the coefficient? For this case, your coefficient, let's write it in red. The first coefficient, the component that is on the far right left hand side, which is ethanol, has a coefficient of 1. Your product, which is acetaldehyde, this is acetaldehyde, has a coefficient of 1. Your hydrogen also have a coefficient of 1. So the number that is in front of the formula, the formula of your chemical is the coefficient. So in this case, that's your coefficient. Your coefficient is this. That's your coefficient. That's your coefficient. The corresponding heat of formation, you can get it from the appendix. So if you're going to use the third method, which is this is the second method. The third method, if you're going to use the third method, which is using the heat of combustion, you're going to use the heat of combustion denoted by delta H subscript, the cap, the superscript, and the subscript C. You're going to use that because the combustion process will be done using your fuel. So that means your fuel is the product, is the reactant. So you start with your reactant first, which is the product of the coefficient with the heat of combustion, which again you can get from appendix B2 minus the product of the combustion, not the product of the combustion, the product of the whatever reaction you're looking at, times by the product of the coefficient and the heat of combustion, which again you can get from the appendix. So that's two methods. And the first method that I mentioned is His law. So that's His law. You'll be given different equations with the corresponding heat of reaction. You play around with it mathematically, and you end up with the desired equation that you want to calculate your heat of reaction. So that's 3 methods of how to calculate your heat of reaction. So let's go through one example. Let me see whether let me use one of the example that one is already given. Let me use an example that we haven't calculated. Okay, this example. This is ethanol forming acetaldehyde. Oh, I'm not sure whether we have the formula for acetaldehyde, but let's see whether it's available. And this is obviously hydrogen. So we're going to look at it both methods. The first method, the method using heat of formation. I'm going to calculate the heat of reaction for that reaction just now. Okay. I'm going to use the heat of formation for that the coefficient heat of formation. You will get it from the appendix, and that's your reactant, your coefficient, your heat of formation. I'm repeating myself all over again. So let's look at our appendix. Okay, we're going to look at for ethanol. So I'm going to highlight it. That is ethanol. This is not the appendix that I want actually. This is B2. I need to go to B1. So let's look for ethanol. So we have over here ethanol. The heat of formation, that's your heat of formation. So if you go horizontally to that heat of formation, there's two listed values for ethanol. You have the gas and you have the liquid. But we are more interested in what was it just now? Was it the gas or was it the liquid? The equation just now is for, I'm assuming it is vapor. It is vapor, ethanol vapor. So we're going to look for vapor. So look for ethanol vapor. The value is minus 235.51. It's 235.51. So let me jot that down. Minus 235.3. Oops, sorry. Minus 235.31. I'm just trying to remember. That will be the for ethanol. What was it just now? I forgot. Somebody, can you recall?
Minus 235.31.
Yeah, 3531. That's why I need to know somebody to help me. Minus 235.31. The value is going to be small. Thank you very much. And we need to look for the heat of formation for acetaldehyde. I'm doing actually this, we have covered this before. So actually I'm just showing you again so that it will be, you can recall it so that you can recall what we have covered last week. Acetaldehyde. Okay, there is acetaldehyde. And where is the heat of formation? You have only one value. That is for the gas. Minus 166.2. So 166.2, let's go back to that example. Minus, oops, sorry, I need to write it down. Minus 166.2. The unit again is kilojoules per mole. Don't forget the point, the decimal point. Okay. No, the dot over there. Now, the next value would be the heat of formation of, according to the equation, it should be hydrogen gas. So this gas, that's gas. We need to jot that down now, hydrogen gas. And guys, what is the heat of formation of hydrogen gas? Anybody? You should know this.
Zero.
Zero. It should be zero because hydrogen is already in its elemental form. It's already naturally occurring in that state, which is an element in the form of hydrogen gas. So it should be zero. You don't need to look it up in the appendix. You should know it by heart because it is existing naturally in that state already. So you don't have to have a value for it. It cannot be formed anymore. So it should be zero. So now if you use that for all this information that we have, so your heat of formation according to the your heat of reaction, not formation, your heat of reaction for that written equation just now is going to be, let's look at the coefficient in front of the formula. The equation I'm going to write, the coefficient I'm going to write in red. That's 1, and that's 1. So everything is 1. So that's easy to remember. So your product is acetaldehyde and hydrogen gas. So acetaldehyde, let's get that value. That is the value for the heat of formation of acetaldehyde. Plus, again, the coefficient is 1 for hydrogen according to the equation as it is written. That is our equation. This is our equation as it is written. So we're going to follow that equation. The product is acetaldehyde. The product is also hydrogen. It also contains hydrogen. And our reactant is ethanol, gas. So we're going to minus that from the value of ethanol. We have the coefficient in front of ethanol, which is 1. And the heat of formation of ethanol is 235.31. So if we do the calculation, what is the answer, guys? I don't have the answer here because you're supposed to calculate it. But I don't have the answer here because you're supposed to calculate the value for the heat of formation. What is the answer? After you have plugged it into your calculator. It's going to be positive because this is the product is the heat of formation of acetaldehyde is less than the heat of formation of ethanol. If I'm not mistaken, it's 69.11, is it? Somebody calculate? I did calculate it last night. Minus 166.2 plus, not mine, plus 235.31. Yeah, it's 69.11. Anybody getting a different value than what I got?
The answer, doctor.
Thank you very much. somehow we seem to have the regulars responding, just the regulars, the few. The other keep quiet. I don't know what's happening, whether you are around, whether you are sitting in front of your handphone, whether you're sitting in front of your laptop or your computer. I don't know what's going on. So I just don't know what to say because that's the problem with online learning. So that's one method of getting your heat of reaction. Now I'm going to show it using the other method, which is the heat of combustion. I'm not sure whether we're going to have all the information that we need for from the appendix for the heat of formation combustion. Let's see. The combustion occur from the fuel, so this will be your reactant, your coefficient, your heat of combustion. You don't really need to remember the what product or reactant minus what, because you already the way to remember is quite easy. This is your product from the combustion from the return equation, your coefficient, your heat of combustion. Right, so let's look up our data from the, we need the data, we need heat of combustion, for ethanol gas from the appendix. We need the heat of combustion, not formation. For acetaldehyde gas, we also need the heat of combustion of hydrogen. There will be a value for hydrogen gas because it's not the heat of formation, but it's the heat of combustion. So let's go to our appendix. Okay, heat of combustion for acetaldehyde. Yes, we have it over here. Yeah, 1192.4. Somebody remember it for me so that I can write it down in case I forgot. 1192.4. That is acetaldehyde. 1000. Is it negative, guys? I forgot whether it's negative.
Yes, yes, sir.
It was negative. Thank you very much. Okay, now ethanol. Let's go back to our appendix. That was just now negative. Thank you very much. Now let's go to ethanol. I have already highlighted ethanol. So now we need to go to the heat of combustion for ethanol gas. Wow, the value is quite high, isn't it, compared to the heat of formation? It's negative 1409.25. Somebody please remember it, negative 1409.25. Oops. 0.25. So use per mole. Next, for hydrogen. Oh, I got it wrong. I got the wrong. This is for ethanol. I need to go and look for hydrogen. Let me erase that. Okay, that is for acetaldehyde. Next, we're going to look for hydrogen. So where is hydrogen? We need to highlight hydrogen. That is hydrogen. The heat of combustion is negative 285.84. Right, negative 285.84. Negative 285.84 kilojoules per mole. So now everything is there. Plug it into the equation for the heat of reaction. We have our reactant. So your reactant, now let's go back to the equation, to the chemical reaction equation. Your reactant is ethanol. So let's put in the value for ethanol. First, the value of ethanol, the heat of combustion of ethanol is minus. First, put in the coefficient, the heat of combustion, and that is for ethanol, for your reactant, minus your product. You have two products. You have hydrogen being formed. You have in the written equation. In the written equation, don't worry about the process. We're not looking at the process. We're not looking at this process. Whether there is hydrogen there, whether there is no hydrogen, don't worry about it. Just look at the equation, the chemical equation, because we are interested in getting the heat of reaction. We are not looking at the process. We just want to know what is the heat of the reaction for that written equation, for that equation for the reaction. So the reactant is acetaldehyde, not the product, sorry. The product is acetaldehyde and hydrogen. So we're going to put that inside the equation. For acetaldehyde, the coefficient is 1 minus 1192.4 plus the other product, which is hydrogen. The coefficient is 1 For hydrogen is minus 285.84. Close the bracket and see whether we end up with the same value that we got earlier, which is 69.11. But using a different method, which is heat of combustion. So whether we're going to get that same value, you can double check. You can plug in the values in your calculator and see whether you get the same as 69.11 kilojoules per mole. You should, regardless of whether you're using heat of formation or heat of combustion, you should be getting the same value. Or somebody? Let me also do the calculation. Minus 1,409.25 plus 1,192.4 plus 285.84. Wow, it's slightly different, guys. What did you get?
I got 68.99.
Yeah, same with me. 68.99. It's not exactly the same, but round it off, you will get it approximately 69. If you round it off. But will be a slight different, but not significant. Okay, between the heat of formation and the heat of combustion method. Slight different, but not that different. Okay, any questions on how to get the heat of reaction? Okay, no questions? That's one example that we have looked at in how to get the heat of reaction. You must have the heat of reaction if you're going to use the heat of reaction method to calculate the energy balance. If you're going to use the heat of reaction method to calculate your energy balance, which I did cover last week using one example, and I'm going to continue today doing another two or maybe one more example, you need to have the heat of reaction. The heat of reaction need to be available, should be given, should be specified explicitly, or you can calculate it yourself. If you're going to use heat of reaction method. So when you're going to use your heat of reaction method, the equation is, according to this equation, this is your heat, rate of heat, that is your change of enthalpy. It's going to your extent of reaction. You need to have your heat of reaction. That's your heat of reaction. Okay, that's the heat of reaction. Then you have what you have covered in chapter 8, out the number of molar flow rate times by specific enthalpy minus the summation in the molar flow rate times by the specific enthalpy of all your components. When you look at the process, now we'll be looking at the process. We'll be looking at this process. We are done with the equation, the chemical equation we are done. So now we'll be looking at the process. So when you look at the process, then you'll be using your energy balance. Okay? So in this example, I'm not going to do this example yet because initially it was asking for calculate the amount of the product, which we did. The first example that I did when we start this chapter 9 was to calculate the molar products of this process. We have got the values. What actually for this example 953 is supposed to calculate the outlet temperature. I'm not going to do that yet. I'm going to look at another example. Yeah. So we're going to look at how to do our energy balance using the heat of reaction method. So before that, let's go through the process that we have to, the steps in order to get your heat of your energy balance. What step that you need to go through in order to solve for the energy balance when there is chemical reactions involved. So let's go through the steps. I did mention last week the steps. They are very standard steps. First thing first, when you come across any process, you need to draw and label your flowchart. Okay? You need to label your flowchart completely. Do not eliminate any information. If there is composition there, write down the composition. The composition should be listed in mole fraction or mass fraction, should not be in percent. Please note that, and have a basis for your process. There should be a basis. Okay? Do the material balance. Calculate what's the product based on the equation given, based on the conversion given, the fractional conversion, percent conversion given. Calculate the product. After that, once you have managed to get everything on the material balance, then you start to look at your energy balance. When you do your energy balance, you have to have a reference state. And when you use the heat of reaction method, you are limited to your reference state. If you are using your heat of reaction method, your reference state is going to be, because you're going to use the heat of reaction in your equation. Your equation is going to be, according to this formula, there is your extent of reaction there. So you're going to have this equation that you need to solve. I wrote it again all over again. I'm going to write it down all over again. Right? So if you're going to use this equation, you are limited to the heat of reaction. And the heat of reaction is normally at 25 degrees C to 180 M. So you have no choice if you're going to use the heat of reaction method to solve your energy balance. Heat of reaction method, your reference state must be all the components involved, all of the components that are in your process, all, whether they are listed in the equation, in the chemical reaction, or whether they are in it, they are not in the chemical reaction, it doesn't matter. You have to write down all the components, whether it is in its elemental state or whether it is a compound. You have to write it down, the phase, what phase is it in, the temperature should be 25 degrees C and the pressure should be 180 M. You are restricted to that. Okay, what I need to point out is you need to write down all the components that is in the process, not only that is written in the chemical reaction, in the equation of the reaction, but it should be also in the process. Sometimes you have a component that is not it's not written in the chemical equation, but in the reaction, in the equation that is involved in the reaction, but it is there as an inert in the process. So you still have to write it down. The thing is that when it is an inert, that means it is not involved in the chemical process. I mean, the chemical reaction, it is not involved. For example, you put in A, but the process is, it doesn't involve nitrogen. You put in A, but there is nitrogen in A. Nitrogen does not involve in the reaction. Only oxygen is involved in the reaction. Nitrogen doesn't involve in the reaction. So your inert, you can choose it at any temperature you desire, any temperature and any pressure. But it would be better to have it either at the inlet condition or outlet condition. Yeah? If you have it in the inlet condition, you don't need to calculate the enthalpy at the inlet. If you have it at the outlet condition, you don't need to calculate the enthalpy at the outlet, because automatically the specific enthalpy will be zero if it's at the inlet, or if it's if the reference state is at the inlet, then the enthalpy will be zero at the inlet. You don't need to calculate it. Then you are only left with calculating the other enthalpy, which is the outlet. Okay, so the component that is in the reaction, or in the equation is restricted by the heat of reaction. So it should be at 25 degrees C and 180 M. Any inert can be at the inlet or the outlet condition, the reference state. Okay, so that's the thing that you need to remember. So once you have done you need to construct your table, your inlet outlet table of your components, and you fill it up using either the polynomial equation from appendix B2, or you have it listed in appendix, for example, B8. So you can get it, it's available. You just plug in the value from the get it directly from the given data available. So it's up to what is available. Okay. Once you have everything filled out, then you start to use this equation to calculate your energy balance. Okay, let's look at an example. Let's look at one example. This is one example. The standard heat of reaction is given. Whenever you have the standard heat of reaction given, automatically you know that you're going to use the heat of reaction method. Another hint is that the reaction should be only one. You only have one reaction. You don't have multiple reaction. Then you know you're going to use the heat of reaction method. So this only one reaction here. Right? So let's put in the, what do we have? This is propane gas reacting with oxygen to produce carbon dioxide, liquid water. This is a combustion process. This is a combustion process, guys. It's a combustion process whereby the water being formed is liquid. Okay, the water being formed in the equation. The water that is written in the equation is liquid phase, but the water that is formed in the process is vapor. Okay? That is vapor. There's two things here. So you have two methods actually on solving it, but I'm going to show only one method. The other method, I will discuss. Just tell you how to do it. Okay, so now, what is the heat of reaction? If I'm going to use the equation, the vapor as the product of this process, then I'm going to have another equation, propane gas or being burned with oxygen gas forming carbon dioxide. Make sure your equation is balanced. Please check the equation whether it is given or is not given. You should check your equation whether it is balanced. Okay, so this equation is balanced. It should be. You have 3 carbon over here, so it should be 3 carbon. In the product, there is 3 carbon. So in your reactant, there should be also 3 carbon. You have 8 hydrogen atom in your reactant. There should be also 8 hydrogen atom in your product. So just check whether it's balanced. So now, the only difference I'm going to do now is I'm going to write this as vapor because I have a vapor being formed here. So what is my heat of reaction? So what is my heat of reaction? I need to calculate my heat of reaction. I have the one written here for liquid water. I need to get it for vapor, water vapor. I need to calculate it. So remember last time I did mention to you guys, let's go back to our notes here. I did mention in the heat of combustion, subscript here. Okay, this is the subscript. Whenever you want to change from liquid to vapor, yeah, in the equation from liquid to vapor, you have the heat of reaction for that written for liquid water. You wanted it to be water vapor, so you have to add in this. Let me erase this. Right. You have to add in this information to you have to add that value to your heat of reaction. And you have to add in that 44 times 44.01 times by the number of the water being formed for every mole of, let me highlight that, that's your NW, the number of water being formed for every mole of your fuel that is being burned. Right? So you should add that value, which is 44.01 NW to whatever heat of reaction that is given when you have water being formed as liquid. When you want to have the heat of reaction for water being formed as vapor, this is what you have to do. You have to add in this extra value of 44.01 NW, and NW is the mole of water being formed per mole of fuel being burned. So let's go back to that example just now. We have our vapor in the product. We have a vapor in the product. So we're going to write based on the equation of the equation for the reaction, whereby you have vapor in the product. So what is that heat of reaction? So I have over here my heat of reaction for when liquid water is being formed. So my heat of reaction when water vapor is being formed. Better not to write that down actually. It might be confusing. So like erase this. Okay. So it's equals to the value that is when liquid water is being formed plus 44.01 NW. And NW is equals to mole of water per mole of fuel. Okay. So your mole of water, let me highlight it, that's 4. Your mole of water is 4. Your mole of fuel, 1. So that's going to be 4, let's write it over here, 4 over 1. Okay, so that's 4 over 1. So we're going to have this equation, the value will be minus 2,220 plus 44.01 times by 4. So what answer will you get? You can reduce per mole. Let me also calculate that we can double check our answer. Minus 2,220 plus 44.01 times by 4. That gives you a value of minus 2,443.96. Anybody getting a different value than my value, calculated value? Anybody?
Yes, same.
Same. Okay, so now I'm going to write that down beside my equation. Minus 2043. I'm going to erase the unit first. 0.96 kilojoules per mole. That's the value that I want. I'm going to erase this part. I already managed to get the heat of reaction for my desired equation. My desired equation. The first equation, I don't want it because I have liquid water being formed. Now my desired equation is the second equation where I have water vapor being formed. Why do I need to have water vapor being formed? Because in my process, I have water vapor being formed. Okay, so now we have already the material balance. The material balance is completed. You don't need to do the material balance. You know, looking at the process as it is drawn here, you have the block diagram being done for you. It's completed already. You have the product, the amount of product being formed is already there. You don't need to calculate the material balance. Why is there? Because this is just to show you how to calculate the energy balance. But when you have the test, definitely you need to calculate your material balance. Okay, now let's go to our first step. We already calculated the diagram is there. Basis, let's say use the basis 100 mole per second of propane gas. That's your basis. Next, you need to draw your table. You need to construct your table. So in our case here, our component there is propane, your oxygen, nitrogen, and carbon dioxide, and water. So let's construct our table. I have propane, C3H8. And let's scroll up. I have oxygen. I have nitrogen. I have my carbon dioxide. And lastly, I have my water vapor. This is water vapor. So, let's see. My propane is in a form of a gas. It's nice to write that down because sometimes when you need to use your appendix B2, you have two equations that you need to look up. I mean, you are given two equations of polynomial values. You need to know whether it's liquid or whether it's gas. So it's better to write down your phase in your table. That's gas. Carbon dioxide is also gas. Okay, the amount of mole molar flow rate coming in, mole per second. Your enthalpy, specific enthalpy, that will be kilojoules per mole. This is what we have done so far. Nothing new here. Your number of mole, this should be in, this should be out. That's mole per second. And lastly, you have, let me undo that. I'm trying to get a straight line. Oops, getting worse. Okay, specific enthalpy out, kilojoules per mole. Okay, not a good job there. I think I can do a good job if I, okay, there we go. And now, what do we have? Look at the block diagram. I'm going to zoom out. We have propane coming in 100 mole. We don't have any propane in the product. So we're going to put a dash. There's no propane present in the product, so there's nothing to be listed there. We have oxygen 600 mole per second in the reactant. We have nitrogen 2256. That is given in your block diagram. You have no carbon dioxide in your reactant. You don't have any water vapor in your reactant. So the rest will be from the product. So what do we have? For oxygen, we have 100 mole per second. For your nitrogen, again, if you have to do the material balance, automatically there shouldn't be any, your number of nitrogen should be the same in and out because it doesn't involve in the reaction. Have a look at your reaction. Have a look at the reaction. There is no nitrogen at all present in your reactant, neither is there in your product. So nitrogen is not involved. Nitrogen is just an inert in the process. So whatever goes in should goes out. That is for nitrogen. So now let's look at your carbon dioxide being formed. That's 300 from the block diagram. From the label block diagram, you have water vapor, the amount of water vapor 400 mole per second. So we have to calculate the enthalpy of H1, H2, H3, H4, H5, H6, and lastly H7. You have to calculate that. So your reference state means a lot because if you choose the wrong reference state, you have a longer process of that you need to go through. You have a longer calculation that you have to do. If you choose it wisely, your reference state, you can save yourself lots and lots of hassle in tackling this problem. So reference state is very important. So what reference state are you going to choose? But then just like I specified just now, you don't have a choice. Whenever you use the heat of reaction method, because your heat of reaction is at 25 degrees C, 1 atm, okay, now you should be your reference state should be based on that temperature and pressure only for the component that is listed in the equation. Only for the component that is listed in the equation. So if you look at this equation, you have, this, okay, that should be C. Your listed component, you have propane, you have oxygen, you have carbon dioxide, you have water vapor. So these are the components that should be at 25 degrees C and 1 atm. Your nitrogen is no way written in the equation. So your nitrogen, you have the freedom of choosing either the inlet or the outlet condition as the reference state for nitrogen. So let's write that down. Your reference state, propane, gas, your oxygen, gas, your carbon dioxide, gas, and your water vapor, gas. These are the components that are listed in the equation. So should be at 25 degrees C and 1 atm. And for your nitrogen, because I don't have enough space, so for nitrogen, I'm going to write it down. I'm going to write it somewhere here. Nitrogen gas, I'm going to write it at the inlet condition. So at 300 degrees C and 1 atm. And your nitrogen is over here, and it is at 300 degrees C, 1 atm. So your nitrogen, I choose it the component nitrogen, I choose it to be at the inlet condition, the reference state for nitrogen at the inlet condition. So if I choose it at the inlet condition for nitrogen, my enthalpy H3 should be 0. Because that's where the condition of the reference state is at. So it's going to be 0. Another enthalpy that is going to be 0 is for propane. If you have a look here, your propane is at 25 degrees C, 1 atm. So that propane is at, sorry, I'm going to clean it up. Let's see. Your propane is at 25 degrees C, 1 atm. So since your reference state is also at 25 degrees C, 1 atm for propane, so I'm going to give it a value of 0. So that solves 2 problems. 2, I don't need to calculate H1 and H3. The rest, I do need to calculate. Okay? So another thing that you have to look at is that these components that I have written here, they are gases. Liquid water vapor is a gas, a form of gas at 25 degrees C. So you know there is table B8 that is available that you can use to get your enthalpy, because the reference state for that enthalpy, that table B8 is the same as the reference that we are using now, 25 degrees C and 1 atm. So we're going to look at appendix B8, so that we don't need to calculate, we just plug in, we just get the values from appendix or table B8, because it is given in that table having the same reference state as what we have for our process. So let's go to B8. So far, any questions? Anybody, any question? Wow, it's 9:41 already. Where is B8? I did not even get you guys for rest, for break, because just now we started quite 5 minutes late. So where is B8? So now it's coming. Okay, there is our B8. That's B8. We have just now inside our process, we have oxygen, we have nitrogen, we have water vapor, we have carbon dioxide. Okay? The value, the temperature, let's go back to that example. Example, we have the temperature at 300 and 1000. So let's go to 300 and 1000. So let's go back to that appendix. Appendix 300 and 1000. So I'm going to just highlight, that's for oxygen, that's for nitrogen, that's carbon dioxide, that's water. And for 300 degrees C, I do the same thing. Yeah. Now let's go back to our example. I know I have at 300 degrees C, I know I have oxygen and I have nitrogen. So for oxygen, 8.47 from the value from appendix B8, 8.47. So I'm going to write that down. Oxygen, 8.47. For nitrogen, I don't have to write it down because I already specified my reference state to be the inlet. So it's automatically 0. I don't have to look it up in the appendix B8 because I already specified that my nitrogen is at 3, the reference state is at 300 degrees C, 1 atm for nitrogen. So that's why it is 0 here. Okay, so now let's go back again to our appendix. We need the values of H4, H5, H6, H7. They are all at 1000 degrees C. Now let's look at oxygen and oxygen first. For oxygen at 1000, 32.47. I'm going to write that down. 32.47. That's from appendix B8. For nitrogen at 1000 degrees C, nitrogen at 1000 degrees C is 30.56. I'm going to write it down, 30.56. For carbon dioxide at 1000 degrees C is 48.6. 48.6. Yeah, and lastly, for water vapor at 1000 is 37.69. completed our table. Now all you have to do is write your energy balance. You should actually write the full energy balance equals to your enthalpy change, your change in kinetic energy, your change in potential energy. We're going to ignore potential energy, kinetic energy, and shaft work. Give a reason why. Because you need to give a reason why you drop these terms off from the equation. So now we have this. Finally, the two terms left. Your heat rate of heat equals to the change in the enthalpy change, and that is equals to the extent of reaction times by the heat of reaction plus your summation out and enthalpy in your molar rate and your specific enthalpy. So what is the extent of reaction for this equation, for this reaction, for this process? Anybody, what is the extent of reaction for this process? The equation is mole consumed or reacted divided by the stoichiometric coefficient of that component. So let's look at just look at propane. Okay, propane is coming in at 100, but there's none of it in the product stream. So what is the extent of reaction, guys? Anybody? What is being consumed? How much is being consumed of propane?
100%.
Yeah, no, we're not talking about percent here. We're talking about extent of reaction.
100 mole.
100 mole. Okay, what is the coefficient of propane in the equation?
1.
1. We're looking at equation number 2. Okay, so it should be 1. So your extent of reaction is 100. So now everything is there. Put it inside this equation. Q is equals to your change of enthalpy. Your extent of reaction just now is mole, 100 mole per second. That's 100 mole per second. I'm going to write down the unit first. For this, I'm not going to do it. Your heat of reaction is for equation number 2. Because we used this now for our water is vapor. So we're going to look at equation number 2. Equation number 2, our heat of reaction is negative 2043.96. Negative 2043.96. The unit is your joules per mole. I'm going to cancel your mole. So that is the first part, this part. So now we're going to look at your table. Okay, your product, you have oxygen, nitrogen, carbon dioxide, and water. So let's write it down. For oxygen, 100. I'm going to zoom out so that we can see the whole thing, or the whole table is visible. That's 100 for oxygen. For nitrogen, and by its specific enthalpy, 3.56. I'm going to write it over here. Plus your carbon dioxide, and by its enthalpy, plus your water vapor, and by its enthalpy. And now everything is there for the product. Now you're going to deduct it from the reactant. Not the reactant, the inlet. You're going to get the inlet. You have propane, 100 mole, but the enthalpy is 0. You have your oxygen, 600 mole per second. The enthalpy is 8.47. And lastly, it's going to be for your nitrogen, but I don't have enough space, so I'm going to put it down here, 2,256 times by its enthalpy for the inlet. So everything is there. Calculate your heat, that rate that you need to supply or remove from the reactor. So let's do the calculation. 100 times negative 2043.96. For that first term, it's going to be, of course, it's going to be 2043.96 because we time by 100. Now the whole thing for the product, 100 times 32.47 plus 2256 times 30.56. Guys, please calculate too, because I might make a mistake so that you can double check my calculation. 400 times 37.69. And that's give me 101,846.36. That's my product. Now not my product. That's my outlet. Right? Now my inlet, I have 600 times 8.47. That gives me a value of 5082. What is the final value for our hit rate? It's going to be minus 204.96 plus 101,846.36 minus 5,082. Finally, we're going to get minus 107. I'm right, guys. Check my calculation. Did I got it right? I think I got it wrong. Somebody check my calculation.
Doctor, I think the heat of reaction should be positive, not negative.
Positive?
Not sure actually.
This one? Positive? It's negative, guys. It's negative. It's negative. Oh, it's my clock is not the same as, okay, it should actually now is 9:15. I thought it's only 9:41. Okay, let's check this. Maybe I did it wrongly because I think that the answer is wrong here. Let's do the calculation all over again. 100 mole of the amount that is being consumed. The external reaction is correct. The external reaction is 100 divided by 1, that's 100. My answer, I'm not sure whether you're going to get the same answer as this. This is propane. I did the calculation last night. I got a different value. That's why I suspected I got it wrong now. Okay, guys, can you check your calculation whether mine is wrong? Let me redo this again. My extent 20 minus 2043. Let me redo everything so that I got everything right. I check all over again. I know that that's not the correct answer because I did it last night and I got a different value. So let's do all over again. Let's check. There we have 100. Let's check everything. 100 times 32.47. That's correct. 2,256 times by 30.56. That's correct. 300 times by 48.6. That's correct. 400 times by 37.69. We got that right. Okay, now the only thing on the inlet that we need to worry about is the 600 times by 8.47. That's correct. Okay, so let's do the calculation all over again. Minus 2043.96. I don't need to calculate that actually because it's times by 100, isn't it? Minus 2043 times by 100 is 960, isn't it? Times by 100. Times by 100. Okay. Say minus 2043.96 times by 100. Okay, that's correct. So now I need to do the calculation for the outlet. 100 times 32.47. Need to check my slide, the one that I have in my notes, because I have this written in my note actually. Let me go through it first so that I know everything is correct. Okay. Okay, 8.47 is correct for oxygen. My nitrogen, I listed it as at 300 degrees C, 180 M, so the enthalpy should be 0. That's right. Oh, guys, I know what's wrong.
The outlet nitrogen,
The nitrogen, the reference state is wrong.
it should be integration.
Yes, it should be integrated. Okay, now I know what's wrong. Look, I have it written over here, 300. But what I did, I looked it up in the table, Appendix B8. And that table, the reference state is not at 300. The reference state at the table is 25 degrees C. That is for B8. And yet I'm using the reference state I listed here, 300. This really makes the difference because Appendix B8, the reference state is 25 degrees C, 180 M. But I've specified that it should be at 300. If I'm going to use 300, I cannot get this from the appendix because that appendix, the reference state is not at 300. The reference state for the appendix is 25 degrees C. So if I'm going to use 300, I need to integrate. I need to get from 300 degrees C to 1000 degrees C using the CP of nitrogen gas from appendix, which is the appendix of B2. This is H5. Okay, H5. That's when I pointed out earlier, the reference state, the choice of your reference state make a lot of difference. It's very important that you choose wisely because in this case, just like what I have done now, I'm actually showing you an example of making the wrong choice. Okay, if I choose 300 degrees C as my reference state for nitrogen, of course it makes a different, it makes it easier to get H3, but now I have to calculate, I have to do a longer calculation for H5. I have to do the integration. Then I need to get the value of my polynomial equation from appendix B2, whereby I have 8 times 10 for minus 3, you know, this thing, plus B times 10 minus 5, plus C times 10 minus, 8, plus D times 10 of minus 12, and dt. I need to integrate that. That make it more of a hassle. So now I'm going to choose wisely my reference state. So I'm not going to choose the inlet as my reference state for nitrogen. I'm going to choose the same reference state as the one in appendix B8. So I'm not going to choose 300 because I'm already going to have to do, I have to do the integration. I don't want that. Even though I already make my life easier by making it the inlet condition whereby my enthalpy is 0, but that is not going to make it easier to get the outlet enthalpy. So I'm going to I'm going to erase this. I'm not going to have that. I'm not going to do this. Okay, that's 30 make it black. That's 30. So I need to have a line here. Okay, I'm not going to have at 300. I'm going to have it the same as appendix B8, 25 degrees C, so that I can use that value from the appendix. Now let's get the inlet condition for nitrogen. Nitrogen is at 300 at the inlet. So I'm going to find the enthalpy of H3 from the appendix now. 300 for nitrogen, 8.12. So that's going to be 8.12. 8.12. It's easier to get from the appendix because now everything is available. I mean, everything is available from the appendix. So you just need to make sure that your reference state is the same as the appendix. That's very important. Even though I said earlier, you can choose your inlet to be in the inlet and the outlet. But in this case, because you have data from B8, it's better to use the same reference state as that from appendix B8. So everything is there. So now change our inlet value for nitrogen. Change this. That is going to be 8.12. Because I did this last night, I know it's not the right answer just now. So now it should be correct. So do the calculation, guys. Let's do it together so that we can see whether we arrive to the same answer. It's very, very important to have the right reference state. That really can make it easier. Oops, I've got an error here. 100 times 32.47 plus 2,256 times 30. Anybody already managed to get an answer? Somebody who has calculated it? Anybody managed to get an answer?
Doctor, I got minus 125,950.36.
Okay, minus 125.
Uh, 950.36.
950 times 10. Sorry.
0.36.
Point. Okay. Sorry, that's 1,000. Okay, let me undo that. So it was 1 point. Is 125. Can you repeat that again, please?
950.36.
950.36. So if you put it in the engineering wise, 1.26 times 10 to the power of 1, 2, 3, 4. That's 2, 4, 5 kilojoules per second. Yeah, guys, I think that's the correct answer because I did it earlier and I got that same answer. Yeah, so that should be the way to do it. Yeah, that's the answer. So the rest you calculate yourself. That's the correct answer. That's the correct answer. Let's just write that quickly. Rate of heat loss is negative. Remember the negative sign because that's implied a lot. The negative sign implies that it is exothermic. So for the reaction to occur, obviously, it's a combustion process. Of course, you're going to release lots and lots of heat. The amount of heat being lost is 1.26 times 10 to the power 5. That's the amount of heat being lost. And that's what they normally do in a power plant. You get your fuel, in this case is propane, you burn it, and you release lots and lots of energy. And from that energy, you use it to turn the turbine, and that turbine will produce electricity. So this is an example of a combustion process. So this is one example of an energy balance that you need to do using heat of reaction. This method is using heat of reaction. You need to have your heat of reaction available because you have this equation that you need to use in order to get your energy balance. You need to have your heat of reaction available. And again, I need to stress this out that your reference state, the choice of reference state, if the component that are listed in the chemical reaction that is written down in the chemical reaction, the reference state must be at 25 degrees C and 180 M. The state must be the same as that written in the equation. It should be gases, then it should be written as gases. Okay, but if it's inert, you have a freedom, either inlet, outlet, or at 25 degrees C and 180 M, depending what you prefer. What is available. If there's data available, then choose that reference state the same as the data that is listed in the table. Okay? So just now I made that mistake, and alhamdulillah, with that mistake, we can see it become a hassle when I choose the inlet as the reference state for nitrogen. Even though my enthalpy is 0 at the inlet, but I have to integrate the polynomial equation from appendix B2. That just add extra calculation, and I might make a mistake in that calculation. So it's better off if I use appendix B8, where I have nitrogen available at 300 degrees C and also at 1000 degrees C. So I better use the reference state the same as appendix B8. Any questions, guys? Anybody? Any questions? It's 9:20. What's the time? 9:28 now. Here in Skudai. For those in UAE or in Yemen, it's in UAE is about 5:28 in the morning. Not sure whether it's Fajar time.
Not yet.
Not yet.
5:40 is Fajr.
5:40. Okay, so you'll be breaking off at 5:40 for Fajar, but in Yemen, it should be already Fajar. Should be not yet. It's 1 hour behind. 4. It's
Yeah.
already 4:28. Yeah, it's now
Yes,
tahajud.
what the-
Yeah, it's tahajud. Okay, guys. Any question on this example? Any questions? Any questions? No? No question? No question at all? Too long, isn't it? Very long. But actually, it's not. This is easy because you have your data available from Appendix B8. You don't have to integrate. This is considered one of the easy problem. You can get it. You can get your data from Appendix B8. So it's just getting it directly from the appendix. This is considered one of the easiest one. Yeah. So if there's no question, let's proceed to another example. Because we will proceed so that we finish earlier. If we don't have any other questions, we finish earlier. Then, oh yeah, I forgot. I need to mention to you guys now the other method. I need to mention to you guys. If you guys are going to use the first equation, you're not going to use the second equation. You're not going to use the second equation. Oops. You're not going to use the second equation, but the first equation, the one that is given. But your product is vapor. Your reaction is liquid. You have liquid here. How to go about it? You have to come up with your hypothetical path. Okay? You start your reference state will be not vapor. The water will not be vapor. The water will be liquid. Let me do this. The water should be liquid because your equation has water as liquid. Is your what inside the written equation has water listed as liquid. So your reference state for water must be also liquid. Must be the same as that written in the equation. So now, if it's liquid, you cannot use appendix B8. That value should not be obtained from appendix B8. Because this is no longer vapor, this is going to be liquid. The water vapor is liquid. Sorry. Your water vapor here in the table is still vapor. It is still vapor. Why? Because that's the one listed in the process as vapor. Yeah, that's vapor. But your reference state is liquid. Sorry, let me highlight this. This is liquid. Your reference state is liquid because that is listed in your equation. Let me rephrase that again. Your reference state is going to be liquid as it is written as liquid in the equation. But in the table that you constructed, you're going to write it as vapor. Why? Because your product is coming out as water vapor. So your table is going to be listed as water vapor, yeah? But your reference state is going to be liquid. So you have to come up with a hypothetical path to get the enthalpy of your water vapor. So you start with 25 degrees C, 1 atm. The water, the phase of it is liquid. You go to 100 degrees C because you're going to change it to vapor at 1 atm. Liquid water, change it to 100 degrees C again, but vapor, 1 atm. After that, you go to your final products, the condition of your outlet, which is 1000, 1 atm, and water vapor. The condition of your outlet is at 1000 degrees C, 1 atm. And that phase is vapor. So now you have to get that enthalpy. That enthalpy is actually for the enthalpy of water, which is H7. Here you start at enthalpy here is 0 because that is your reference state, liquid water. Your reference state is liquid water at 25 degrees C, 1 atm. So you start with that reference state. So your enthalpy is 0 there. So you have to calculate that the H1, that the H2, which is the latent heat of vaporization of water, at the normal boiling point and at the H3. So finally, you get H7 is equal to the sum of the overall process. So that is how you calculate when you use the original equation, where the product of the water form, not the water form, the written for your the written equation listed water as liquid, but your product is vapor. So you end up having to calculate your enthalpy for H7 using the hypothetical path. It's a matter of choice. Which one do you prefer? You use the hypothetical path, you don't need to calculate for the second reaction, the heat of reaction for the second reaction. If you prefer using the second reaction just now, then you don't have to use the hypothetical path. You can get it directly from Appendix B8. So it's a matter of choice. Both methods will give you the same answer. Any questions? Yeah, let me stress on this. Whatever is written, whatever component is written, the component should be listed as it is. Then it should be at 25 degrees C because your heat of reaction is at 25 degrees C, 180 M. So your reference state should follow your heat of reaction. And the component should be listed as how the equation are written, as how the equation is written, as how the component are written in the equation. Right? So it should be listed as such. For my example just now, I wrote a new equation whereby I have water as a vapor phase. Then I need to calculate the new heat of reaction. That's what I did just now because I don't want to do the hypothetical path. So that's another method. But if you don't want to use the second equation, use the original listed equation, then you have to write down your reference state should be liquid water as it is written in the equation. Okay, then you have to draw yourself your hypothetical path going to the vapor phase of your water. From liquid going to the vapor phase. You need to draw your hypothetical path. So it's very important whether you want to come up with another equation whereby you have water vapor, or you just stick with the original equation, then you have the hypothetical path. Do not use the appendix B8 if your component water is the reference state is liquid, because appendix 8 is only for gases, not for liquid. Right? Any questions? Okay, now just now we were looking at this problem, this example just now. We calculate the heat of reaction. Let me write down the heat of reaction that we just got earlier at the very beginning of the lecture. We got that value 69.11. I'm going to erase this, tidy it up. Now, I'm going to erase this part because I already get the heat of reaction. So I'm not going to use this. We did this example earlier because we want to get the heat of reaction. It's not given. So now the question is, for this example, is to calculate the outlet temperature of your product. What is the outlet temperature of the product? So I need to do the energy balance in order to calculate that value. So let's tidy this up. So far, anybody has any questions? Nobody? Guys? Nobody going to respond? Too tired? Still sleepy? It's a new year. Did you celebrate last night? I hope not, because you have an 8 o'clock class this morning. Okay, guys. The question here asks for the outlet temperature. The outlet temperature, T out. What is the outlet temperature? And it so happened that in this example, you have an adiabatic reactor. An adiabatic reactor is where your Q is equal to 0. Right? So the heat is not being lost to the surrounding. The heat is being used to heat up the product, and also the heat is being used to supply, for example, to turn the turbine. This is an example whereby you have an adiabatic reactor. So the temperature coming out is listed as the adiabatic temperature. The adiabatic temperature, if you have combustion, is normally the highest possible temperature that you can reach in an adiabatic reactor. The outlet temperature, if you have an adiabatic reactor, implies that your adiabatic temperature, the outlet temperature, is the highest possible temperature that you can achieve. So the question asks for what is the outlet temperature. So we have already done the material balance. What we need to do now is our energy balance. So I'm going to construct myself my table. As usual, we're going to construct ourselves a table. Do that. How many components do I have? I'm not getting a straight line here. Let me get a straight line. Why am I not getting a straight line? Let me get a straight line. Trying to get a straight line. Oops. Okay, guys, I think that's a break. Give you guys a break. Oh, it's almost 9:40 already. Oh dear, better not have a break. Just let me ask you guys a question. It's 9:40 already. Okay, here we have ethanol. I have ethanol here. At 300 degrees C. And you have acetaldehyde. Which one is acetaldehyde? CH3 is the acetaldehyde. Okay. We have ethanol, okay, coming out. I'm going to ask you questions. And better, I guess, somebody need to respond. I'm going to ask you guys, what is the extent of reaction for this process? Actually, we got it last time. We have mole of the reacted or mole consumed divided by the coefficient of that component. So the reactant, you should be looking at the reactant. When you look at the extent of reaction, look at the reactant only, not the product. Well, you can look at the product, no problem also. Then if you're looking at the product, then it should be mole produced per coefficient. So somebody, if I'm going to look at, for example, the product of acetaldehyde, if I'm going to base my calculation on acetaldehyde, so what is my extent of, what is the mole produced for acetaldehyde? Somebody, please respond. I'm not going to start the calculation yet. I'm not going to start the example. I'm just going to ask you guys the thing that you already know.
Is it 30?
Oh yes, 30. For acetaldehyde is 30. 30. There's non-acetaldehyde in the reactant. So the mole of acetaldehyde being produced is 30. There's no acetaldehyde in the inlet, only in the outlet. So that's the amount of acetaldehyde being produced divided by its coefficient. What is the coefficient of acetaldehyde?
1.
1.
1.
So your extent of reaction is equals to 1. 30 mole. What is the unit per mole? Just mole. So that is your extent of reaction. Right? So now, if you're going to use your energy balance, the extent of reaction times by heat of reaction, E plus out your mole, your specific enthalpy, minus in your mole, number of mole, your specific enthalpy. So your heat of reaction, we already got it here. Okay, so now just multiply this first part, the first term, 30 mole, and by your heat of reaction just now is 69.11 kilojoules per mole. So that cancel off, you already got the first term. For the next part, you need to draw yourself, you need to construct yourself your table. Right? So we have the number of mole, the material balance is already done. So you need to draw your table. So let's draw our table. I'm not sure. I don't think we have enough time to complete this. but I'm just going to draw the table. We have which roughly I have ethanol, I have acetaldehyde. So let me reduce that further so that I can write down C2H5 OH, that's ethanol. My acetaldehyde CH3 CHO, that's acetaldehyde. And lastly, I have my hydrogen. And in mol, H in, kilojoule per mole. And out, mol. Let me make it bigger. H out, kilojoules per mole. Yeah. So let's list down the amount in our table. We have 100 mole coming in of acetaldehyde. There is no, ethanol. There's no acetaldehyde. There's no hydrogen in your inlet. The amount coming out for ethanol is 70. The acetaldehyde being formed 30, and the hydrogen being formed is 30. So you are left with the unknown H1, H2, H3, H4. Now, my next question. What reference state should I use? My next question. What reference state should I use? There is no inert in this example. You have ethanol, in fact, in. You have your ethanol coming out. You have your acetaldehyde coming out. And you have your hydrogen coming out. And these three components is also involved in the reaction. There is no inert at all. So what is the reference state? How are you going to write? You're going to write your reference state. Somebody answer, please. What reference state should I use? What are the components? What are the states? What's the temperature? What's the pressure?
Doctor,
Mm-hmm.
at 25 and 1 atm,
Okay, what's the component?
ethanol,
What state?
gas,
Yeah.
acetaldehyde,
What state?
gas,
Yeah.
and hydrogen gas.
Hydrogen gas. Okay. And the temperature at 25?
25 and 1
Is-
atm.
Why at 25 and 1 atm?
As is standard or fixed?
Standard what? Somebody? Why at 25? 1 atm?
Because for the heat of reaction, or I mean, this is like we have. I mean, like this is the only option we can take. I mean, for
Okay.
using the heat of reaction formation or reaction.
Yeah, because if you're going to use the heat of reaction method, yeah, you're going to use that equation. Your heat of reaction method, the temperature, your heat of reaction is at 25 1 atm. So whatever component that is involved in the reaction, we will list it as it is written in the equation at 25 degrees C 1 atm. That's the reason why we choose 25 degrees C 1 atm, because we're going to use the heat of reaction method. And the heat of reaction is given at 25 1 atm. So that's the reason. And so now, the next step will be to get the enthalpies, complete your table, then put it inside the equation for your energy balance, and you are done. So this part, you need to proceed further in order to get your solution. Alright. So how to get, for example, ethanol, the reference state is 25, H1. You need to get it from 25 degrees C to your inlet condition, which is 3300 degrees C. And your ethanol is coming in as gas. So you need to get your CP from appendix B2 for ethanol gas, BP. For your H2, again, it is for ethanol gas. It's the same for ethanol gas. It's still ethanol. H appendix 2, but the only difference is that the temperature of your outlet stream is the unknown. The temperature is unknown. You're going to use the same CP for your ethanol gas, but now it's going to be listed as in terms of temperature. The temperature is unknown. You cannot integrate it. So you will have an equation that have the unknown in terms of temperature. Okay, so you cannot get a value there. You're going to have an unknown, an equation, sorry. You're going to have an equation in terms of temperature. The same thing we do for H3 from 25 degrees C. H3, appendix H3 is for your acetaldehyde. Your acetaldehyde, so this is ethanol. Let me just put ethanol. That is ethanol. Acetaldehyde. Then short form. Your T out is the unknown. Then this CP is for acetaldehyde, gas, T. And you do the same thing for water. Sorry, is it water or is it hydrogen? It's hydrogen. You do the same thing for hydrogen at 25 degrees C and T out and get the CP of hydrogen gas with respect to temperature. So for H2, H3, H2, H3, H4, you will not get a value, but you will get an equation in terms of T out. So when you plug everything in, the equation over here, the Q, because it is adiabatic, it is written here adiabatic, so Q is equal to 0. It is equal to 0. So the unknown is T. So you can solve for T. You need to use your calculator in order to solve for the outlet temperature. The unknown is T. You multiply your outlet here. You multiply, sorry, this is your outlet, get the product here, minus by the inlet. And use that equation. Use the equation where your Q is equal to 0. You should be able to solve for the temperature out. Okay guys, any questions? That this part of this example remind me of test number 2. Test 2 asks for the outlet temperature. You use your integration, your calculator, using the integration to get the outlet temperature. This is more or less like that. Yeah. So use the equation and use your calculator to get the outlet temperature. It's quite complicated in a way because you need to have the engineering calculator in order to calculate the temperature outlet. Any questions? Any questions? This problem is using polynomial equation integration. Any questions? Anybody? No? No questions? Okay, guys, since there's no question, we will stop here. Okay. Thank you very much and do take care in this year. Hope everything, everybody is fine. Everybody might get better this year and can come to TM and see each other face to face. Most probably by the end of the semester, I will not be meeting you guys this semester face to face, but should be meeting you guys maybe somewhere in UTM, you know, but not in this subject because the semester ends for this semester is I think in February. You guys are still online in February. Guys, thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Doctor,
Doctor,
Yes. Yes. Oh yeah.
can
Can you
doctor
share the-
display the QR code?
Yeah, I just remember. I need to share the QR code. I don't know what's the problem just now. I need to, hold on, I need to go to my, okay, why am I not getting it? Hold on guys, let me get my QR code first. Okay, now I can share it. Yeah, guys. Okay, somebody managed to scan. 24 of you did. For the rest of you guys that already